All right, guys, so we're going to go ahead and move on to problems 5, 6, 7, and 8. In the box right above them, we talk about the fundamental theorem of algebra, and the linear factorization theorem guarantees that every polynomial function of degree n with real coefficients has exactly n complex zeros. And here I'm only asking you to find all the complex zeros of the following, but really I should have wrote all the real n complex. The thing that you guys do need to understand that a real number is a complex number, because I can write 3, which is a real number. I can write that as a complex number by doing 0i. So by doing this, it actually makes 3 complex. Real numbers is actually a subset of their complex numbers. All right, so let's just kind of dive in and actually solve this and find all of my zeros. First thing I see with the 4x to the fourth and plus 12x squared plus 8 is the greatest common factor is 4, and I'm going to factor that out. So I'm going to say 4 times x to the fourth plus 3x squared plus 2. Now we're actually going to factor this part right here. And we're going to use the AC method of factoring. My leading coefficient is 1. My A is 1. My C is 2. So 1 times 2 is 2. And all of my prime factors of 2 are just really plus or minus 1 and plus or minus 2. I don't need to write those down. There's only 2 options. Then I ask myself, which combination, when I add them, will give me a positive 3? Well, that's pretty straightforward. That's going to be a positive 1 and a positive 2. So I'm going to rewrite my middle term. I'm doing 4x to the fourth plus x plus 2x plus 2. And of course, these are squared. Now we're just going to group them. Make sure your plus sign is in between. And then from there, we're going to have 4 times, and then x to the fourth and x squared has a x squared in common. And of course, when I factor that out, that's going to leave me x plus 1. When I look at my next term, I have 2x squared and 2. Of course, they have a 2 in common, so I factor that out, and that leaves me x squared plus 1. Now, when I look at each of these individual terms, right here and right here, we have x squared plus 1 shared in the term, so we can actually factor that out, and that will give me a fully factored polynomial, 4 times x squared plus 1 and x squared plus 2. Now I could factor this down a little further and actually get imaginaries, but at this point, if we're looking for the roots or the x-intercepts, we actually change our f of x to 0, and we're just going to solve for 0. So we put 0 in here. Really what I need to do is just take each of these terms and set them equal to 0. Of course, 4 doesn't make any sense. It doesn't have any variables. You could divide both sides by 4 and get rid of it, and 0 divided by 4 is 0, and 4 divided by 4 is 1. But really what you just want to do is just do x squared plus 1 equals 0, and x squared plus 2 equals 0. Now when I solve these, I'm going to get x squared equals negative 1, and of course x equals plus or minus the square root of negative 1. If you remember from Algebra 2, the square root of negative 1 is I, which is imaginary complex. So the square root of negative 1 simply becomes x equals plus or minus I. To solve the other side here, we have x squared equals negative 2 by subtracting 2. And then we have x equals plus or minus the square root of negative 2. Well, I can rewrite this as plus or minus the square root of negative 1 times the square root of 2 by using my square root rules. And of course, the square root of 1 is I. So we get an answer of plus or minus I square root 2. So my solutions to these, I have 4 complex solutions, plus or minus I square root 2, which are both conjugates of each other. The I and negative I are conjugates, and I square root 2 and negative I square root 2 are conjugates of each other. There are 4 of them, which is the degree of our polynomial. I'm going to have you guys go ahead and do 5, 6, and 7, and then we'll be moving on.